Okay, guys, let's look at 64. And 64 is talking about the polar form and the complex plane. Now, when we're talking about the complex plane, we're talking about what's called the Argand plane, the complex plane, where this is the real axis, and this axis here is the imaginary axis. Okay, so this is the real, this is the imaginary. Therefore, if I was going to plot a point, -2, that's on the real plane, so it would go -2 steps on the real. And then -4i is imaginary, so it would come off onto the imaginary axis 4 steps. So -2, -4i would be about there. Okay? Now, what we're going to start talking about here is this distance here, we're going to show you here, when we're talking about a polar form, this is rectangular form of the imaginary coordinate. This is a complex coordinate in rectangular form. Okay, rectangular form might be written in x hat, j hat form. I mean, I hat, j hat, excuse me. I hat, j hat. That's one of the ways the book writes it. It can be written like this as an ordered pair, a coordinate. This is your first, your x and then your y. In this case, this is the imaginary plane, so that's your imaginary coordinate. Okay, now this right here, this hypotenuse is necessary to find because we've got to be able to change easily from rectangular form to polar form. And what is polar form? We've talked about polar before, but what is polar form?
IJ. It's
IJ is your rectangular form.
Degree.
Okay. It's the degree, and in your book they will write it like this. They will write your degree inside the little angle, and they will write this right here. What is that right there?
Hypotenuse.
That's the length of the hypotenuse. That is the hypotenuse, or the distance from the point to the center. So if I wanted to find this distance here, this hypotenuse, even though I was on an imaginary scale here, basically this is called the absolute value. Absolute value. Okay, the absolute value is the distance of that hypotenuse. And if I were to find it with just a, what, right triangle, could I say, okay, that's a distance of 2. Okay, so I've got 2, and it's a -2, and I'm going to square it, right? I'm just doing my Pythagorean theorem here, guys. And then this was a 4 down, and it's a, what? -4. Basically, the distance is a -4. Okay, so it's a -4 squared. And so what is that hypotenuse, or that absolute value, going to be? It's going to be what? 4 plus 16 equals 20. And then I take the square root of that, right? So the square root of 20 is going to be what?
2 squared of 5.
2 squared of 5. So 2 squared of 5 would have been the distance there. All right, now look over here at the B portion, and they're just re-describing these things. They're saying, okay, we have a 30-degree angle. 30-degree angle with our, this one is a 30-degree angle blown up a little bit, because remember our special triangle for the 30-degree became what? 1, 2, and what? Okay, your square root of 3 over 2. And then this one was
And 1/2.
1/2. That was 1/2.
And then
okay, and that was 1. So this one is square root of 3. You're right. I was. So this one we multiply it all by 2. That becomes 1. That becomes 2, and that becomes the square root of 3. Okay. So that's our normal, and then they blew this one up. So this is just our special triangle blown up. Okay, to where it's 4, 2, and 2 square root of 3. So when I'm looking at something like that, if I was going to write this point right there, and I was going to put this on the axis to where that was right at 0, 0, then this point right there would be written that way rectangularly, wouldn't it? It would be 2 square root of 3 right, and then it would be 2 up, okay, and this hypotenuse here would not be in this equation, but when I go to write it in the polar form, it's going to be the hypotenuse 4 times the angle 30. So they're just showing you in this section how those two are the same thing. Okay? Now look over here. They're talking about the same thing with the length of the hypotenuse being called the absolute value. All right? And if I'm looking at this is the rectangular coordinate here. Okay, the rectangular coordinate is right there. And if I put that in absolute values, that doesn't mean absolute value the same way we always think about it. It's going to mean the distance between here and that point. So they're redefining this. They are still going to use the absolute value signs. They're still going to call it the absolute value. But when you go to get it, what you're doing is you're taking this distance squared plus this distance squared to get the hypotenuse. Okay? Now when I do that, what happens? I get this distance squared, which is what? 4 times 3 is 12. 12 plus this distance squared, which will be 4. And I take the square root of it, and I get the 4 that they're talking about. Okay? So they're just introducing that concept here. And then, if we were going to write this one...
Isn't it always going to be the hypotenuse though?
Huh?
Because that's just the Pythagorean.
Yeah, it's the
hypotenuse.
hypotenuse.
Always going to be the hypotenuse.
Yes, it's always the hypotenuse. But I'm just saying that's a notation that we haven't seen before. Okay, so then if I were going to use a real, in other words, this is the real plane right here. This is a 2, this is 2 squared root of 3. Then it would be what? 4 onto the angle 30. But if I was doing the exact same problem in the argand or the complex plane, and I had it right here, and this was 2 squared root of 3, and this one was 2i, okay, it's imaginary, but it's going up 2 steps, it's going to be the exact same thing, except we're not going to express it like this. We're going to express it like this, because now we're in complex. And this is saying cosine plus I sine of 30. Okay? And that's the notation that you're going to always use for the imaginaries. Okay? Now, if I looked at that angle here, this cosine here is the real part, isn't it? But this imaginary part here is the imaginary part. So that's why they're saying plus I sine of whatever that angle is. Okay, I means the I was pulled out. All right, so now everybody look over here at 64. See, where we're talking about sums. Okay, sums and products of complex numbers. Okay, now when we're talking about sums, we can only add like terms, right? So we're not going to be able to add imaginary parts and real parts together. We have to get them in their rectangular form to be able to add them. We can't add them in polar form. We have to get them in rectangular form. So if I have a 2 squared root of 3 plus 2i and a 2 plus 2i, I can add them by adding their real parts together and get 2 squared root of 3 plus 2. That's the real part. And then I add the imaginary parts and get what? 4i. Okay, now this one is my I hat, or my real part, and then this one is my imaginary part. Okay, which they're showing you down here when you add them together. Okay, now look at the, they're just showing you at the top. What happens when we multiply them? 2 squared root of 3 plus 2i, 2 plus 2i. Can I FOIL in imaginary numbers? I can, can't I? What am I going to get? Multiply the first, and I'm going to get 4 square root of 3. Multiply the outsides, and I'm going to get 4 square root of 3i. Can I multiply the insides? 4i, and the outsides is
5, 4, and
Okay, plus 4 square root of 3i.
No.
Okay,
No,
now
we already did that. It's the
Oh,
last one.
thank you.
Just 4i
4i squared.
4i squared. What is I squared?
-1.
-1, so that's going to be -4. So we're going to have, when we put it all together, we're still going to put our real parts in the front. 4 square root of 3 minus 4 in the real part, plus 4 square root of 3 plus 4i, and I could factor out the 4, but I have to put those together in the imaginary parts. Okay, now what they're showing you down here at the bottom, okay, is that when I have complex numbers, I can multiply them in their complex form, and I will get the correct answer. It won't look like this, but if I took this and turned it into complex form, or the complex form and turn it back into the rectangular, it would work, okay? And it's very simple to multiply complex numbers when they are in their complex form. We just multiply them in rectangular form. This is the rule. Really cool. If I have 5 and I have cis 20, now they have written it out. They've written out the 5 cis 20 in your book. They've written cosine 20 plus I sine 20 and 6 cis 42. So I'm going to write the shorthand here because they have the longhand in your book. Okay? And when you do that, you're going to multiply and you're going to get 30 cis 62. So what's the pattern?
First 2 multiplied. Then the
We
3
multiply the constants in the front and we add the degrees. And if we turn this back into the rectangular form, and then did it the other way by foiling it, we would get the same thing. Yes?
What's this?
Cosine plus I sine of theta. Okay? So the cosine, remember, is your x part of your, and the sine is your y part of your unit circle.
Okay.
Okay, so the y part is the imaginary part. So they're saying the I times the sine because it's always going to be the imaginary part there. Yes?
How do you go backwards?
How do you go backwards from here to here? You would not always be able to go back to the exact things without knowing them.
So
Okay?
they want that
In other words, basically when you multiply something together and then you go back to factor it, sometimes there's more than one way to factor it. Okay? So when we go this way, it's an absolute. But if I just gave you that and I told you to factor it, it would factor into any number of things. Because I could change
Should
these
they
and
give us something like x times 6 cis 42 equals 36 62? Something like that.
yeah, I don't think they're going to do that though.
Okay,
You're
maybe
going to
one.
see the problems they're going to give you with this. Okay, so those are the two concepts. We have to put it into rectangular to add or subtract them. But we can multiply them in either form, either rectangular or